Welcome back to Maths with Mrs. J. We've started a series of videos about limits and continuity. In my previous video, I did a graphical introduction to continuity and discontinuity. Obviously, if something is not continuous, there's a point of discontinuity. Now I want to introduce the idea of limits from a graphical visual perspective. As I said before, I'm doing this from a high school level perspective, year 11 and 12. I'm not going to go into the proper pure mathematics definition of limits and continuity. I would rather do it from a perspective of a high school student, seeing as though these are the students who I target with my videos. I'm trying to help you understand your year 11 and 12 maths. What I wanted to first introduce to you is this idea of a limit as being a point that you are approaching. So if we're here, we're talking about the limit as x tends towards a of this function. Now you can get closer and closer and closer to this point a from above. We write that as a limit as a tends towards a with a little plus. You can get closer and closer and closer to it from below. We can write that as limit as x tends towards a from below. And what you will notice is as your x value gets closer and closer and closer to a, your y value, if you're coming in from the right, is going to get closer and closer and closer to f of a. That's because this function is probably one of the easiest ones to work with. This function happens to be defined for x equals a and continuous at x equals a. So there's no problem with just basically subbing into the function to get the y value there. As we're coming in from the left, we'll notice also that the function is tending towards, it's getting closer and closer and closer to the value of the function when x equals a. So in a very simple case like this, really the limit is just going to be f of a. However, of course, there are a lot more different possibilities where things get a little bit more interesting. If they both equal each other, then we say the limit exists. And in this case, the limit is just f of a. Here's a little side note. A lot of people get a bit confused, and I can understand why. A function can exist and be defined at a point, and yet the limit not be defined there. But conversely, you can have a function that's not defined for a particular x value, and yet you can calculate the limit there. We're going to have a look at some of these sort of seemingly contradictory situations as we go through these various types of examples. Just a word, when I call it type 1, it's not universally known as a type 1, it's just what I've deemed as, or what I consider to be a type 1 example. I find it's kind of useful to put things into categories. Type 1 is like what we just looked at, a situation where you have a continuous function. This looks like a cubic function. It's continuous everywhere. It exists everywhere. So obviously, if you're coming in from the right or the left, coming in from the right or the left, your function is coming in towards the value of the function at that x value. That's the simplest possible example, and we can just sub in. So they're our nice, easy examples. And basically, if you can sub in, you do. The second type is where we might have had a piecewise function, and either we're looking at the limit at a point where the function rule has not changed. So say we're up well away from this sort of critical x value here, so up at b, and there it becomes a bit like a type 1. You're just going to sub in b to the particular rule that's in play at that particular part of your domain. So for example, say A was at x equals 1, our rule changed from an upside down parabola to a straight line, and say we wanted to know what the limit is when x is 3, well, we'd be subbing into the straight line formula because that's what is in play here. As you're getting closer to B, either from the right or the left, you'll notice that your y value is going to get closer and closer and closer to what you would sub in to that straight line with x equals 3. This point here, we've got the changing rule, but we've got the condition where we've actually got continuity happening. It would not be differentiable there because you wouldn't be able to get a tangent, but that's a whole nother topic. What happens here is that as you're coming in from above and working out what would happen were you to apply that straight line rule to x equals 1, you get the same value as you get if you applied the parabola rule coming in from the left. So regardless of whether the open circle is to the left or to the right, because it joins up, the function there will be what you sub in when x equals 1 into either of the functions really. It's continuous there. So that's kind of like type 1, but it's just a little bit more complex. All right, so you're subbing in either to whichever version of the rule is applicable for the particular domain that you're talking about, or you're realizing that even at the point where the function changes its rule, the value that you're approaching with both functions is the same y value. In that case, you can sub it in. All right, let's look at some slightly more interesting examples. Okay, type 3. Type 3 would happen if you were to have a piecewise function with a discontinuity. If you're trying to find the limit at that discontinuity, then what's going to happen is as you're coming in from the right and using that rule that's applicable for the x values to the right and up to and including the dot there, you're going to get a certain value as your limit, which will be this y value here. It will be the y value from that function rule subbing in x equals a. As you're coming in to x equals a from below, what happens is you're approaching, in this case, this is your open circle, so you're approaching but never going to actually reach this point here. This point here would be the y value when x equals a of that rule. Now, even though that rule is not in play for x equals a, it's an open circle, we know that the function's going to approach that point. Now, what we've got here is the limit as x tends towards a from above is going to be this rule. So we're going to get a certain value, say it might be 5. The limit as x tends towards a from below is down here. It's about, say, 2.5 or something. Even though it's not going to actually equal that, it's tending towards it. We've got to jump. These two limits are not the same. So they are not the same. Therefore, we say the limit does not exist at that particular x value of a. And we have a discontinuity. That's how they kind of link up there. Type 4, I actually did one like this when I did a series of videos on graphing rational functions. This is a very interesting example that you could get were you to be graphing something of the variety, something like x squared minus 4 over x plus 2 or something like that. That's a special case of a rational function where what's happening is if you were to sub in x equals -2, you'd get 0 on 0. But you can factorise and cancel. And really this function is the same thing as y equals x minus 2. Now, obviously, this is not the line y equals x minus 2, but this is just an example. Y equals x minus 2, but with a hole in it for that particular undefined x value. The limit is defined here, but the function is not. So this is an example. So the limit is defined. Remember, the limit doesn't, you don't never have to actually reach it. It's just what you're getting closer and closer and closer to. The function is actually not defined. At x equals a. You cannot sub in x equals a into that original value of the formula, original version of the formula, I should say. You can into what's called the intermediate, or indeterminate, I should say, version of the formula here, and that's how we actually do calculate it. So it's kind of like we say, all right, well, we're saying x can't be -2. We're saying that this is really the straight line y equals x minus 2. So let's sub in x equals -2 and see what it would have been there. All right. That is how we will calculate that algebraically. But for now, just realize that this is actually a very interesting case. You're getting closer and closer and closer to x equals a. You're getting closer and closer and closer to this value here, this y value. Same thing is happening from below. You're getting closer and closer. You're never actually going to reach that, but that is what a limit is. It's saying what is happening as you're getting closer to that x value. What is your y value approaching? Type 5, all right, here we've got obviously some sort of hyperbola. If you're approaching your vertical asymptote from above, have a look at what's happening to this function here. It is approaching infinity, isn't it? So the limit of this one from above is infinity. You're never going to reach infinity. It doesn't exist, all right? But it's heading just ever increasingly positive. As you're coming towards this x value from below, look what's happening to the function. It's going increasingly negative. So the limit as x tends towards a from below, in brackets, will be negative infinity. Now there's a huge discontinuity here, isn't there? You're coming down here and then you've got to lift your pen up and go down there. It is discontinuous at x equals a in a big way, all right? The limit does not actually exist there. If it's going to positive infinity from above and towards negative infinity from below, these two limits are different, and so we say the limit does not exist. Okie dokie, just a couple more to look at. Now I've drawn 4 of these, they're all the same type. I just wanted to show some different versions of the same type. On this slide, what I'm talking about is what's happening as x is tending towards positive infinity and as x is tending towards negative infinity. In other words, what happens to the function as x is getting increasingly large or increasingly small? And what we're really doing here is we're having a look at our function. As x is getting increasingly big, what's happening to the y here? Well, the y value is getting increasingly big. So this one you could write as x tends towards infinity, f of x also tends towards infinity. Another way of writing that would be limit as x tends towards infinity of f of x is infinity. Either of those are equal. Just a little side note, we've been talking about approaching from above and below. We were talking about limit as x tends towards 2 from above or limit as x tends towards 2 from below. The only way you can approach infinity is from below, and the only way you can approach negative infinity is from above. So it doesn't make sense to do left and right sided limits for infinity and negative infinity. This one here, as x is tending towards negative infinity, the function is also tending towards negative infinity. This one here, same sort of thing. As x gets greater, your function is tending towards negative infinity. As x is getting increasingly small, the whole function is tending towards negative infinity again. This one's the opposite. Here we have a concave upwards parabola. As x is tending towards infinity, the function itself is tending towards infinity. As x is tending towards negative infinity, the function is tending towards positive infinity. And here we have a typical cubic example. As x is tending towards infinity, y is tending towards infinity. As x is tending towards negative infinity, y is tending towards negative infinity. I'm deliberately not writing a lot down on this video because we are going to do a detailed video in the next one where we actually have a look at, in particular, points of discontinuity and what's happening as we come in from the right and from the left, and also have a look at some examples as we tend towards infinity. Here's our hyperbola example. Here, as x is tending towards infinity, this line will be approaching this horizontal asymptote, which is y equals k. So for this particular one, as x tends towards infinity, y tends towards k, and it tends towards k from above. All right, it's coming in from above. It'll always be just a little bit more. As x is tending towards negative infinity, we're also going to be approaching this horizontal asymptote. However, in this case, we're going to be approaching it from below. So these little plus and minus can also be used to talk about from above or below. Here we've got an example where we have a vertical asymptote and an oblique asymptote. As x is tending towards infinity here, the function is actually tending towards this line from above. So as x tends towards infinity, y is tending towards that line. So the asymptote from above. As x tends towards negative infinity, we're tending towards the asymptote from above again. In this case, this asymptote itself is tending towards infinity, so this will be tending towards infinity, but this kind of gives it a bound. It will always be slightly above that straight line. It will always be slightly above the straight line here, but tending towards negative infinity. I hope I haven't made it too complicated. I've tried not to. It's really just a matter of thinking about as x is getting bigger and bigger and bigger, or smaller and smaller and smaller, what is happening to your y value? That's for your limits to infinity. For our previous slides, what we're saying is as x is getting closer and closer to that particular value, either if we're coming in from the right or coming in from the left, what is happening to the y value? What is it getting closer and closer to? And that's the way I think about limits. That's the way I think it's a good explanation of how they work. I will be going on to do some examples from graphs, and then I'll be going on to teach you how to calculate limits from the rule, to do it algebraically. So stick around for the next few videos. If you do like my videos, remember to subscribe. I make new videos quite frequently, and they cover everything from about year 7 to year 12.